Welcome back, everybody. Welcome back to the channel. So today we're going to be talking about how to call the main method. So in the previous episode, we talked about part two of how to actually set up the main thread and how to actually start it. And we're kind of here at the start application phase. So we are now joined to the main method and we have successfully started it. Now, if we go into here, into the start, we've already gone over the start function, so I don't have to do that. But now let's look at the virtual machine interpreter thread start function. So this is going to be the main function that you're going to need to create to basically execute the entire programming language. So I think we've gone over this before, but so you want to create an interpreter thread start, pass it a void pointer of an argument, have the return value be a static for Windows, this value, for POSIX, this value, and that's it. And then you want to create this function inside of your virtual machine or whatever file you want to put it in. And now this is going to represent the start of every thread. So this is the lowest level that we can ever get in our programming language, where when we start threads, of course, this is the starting point. So you want to start off by casting the argument to a thread. Once you do that, you want to update the thread self variable because it's going to allow us to be able to access that thread self or the current thread that we're in elsewhere in the source code. And then you want to set the st base and the st floor. Now this is going to be used for the JIT. This is how we keep track of if we are going to overflow the stack basically. So we're going to set the base, meaning that here's the base address or the starting address of where we are in the stack. And the floor is going to be the base minus the total stack size of the actual thread. This is going to be the physical stack size of the thread, whatever value that is. And the way that stacks work at the low level is the numbers go negative. So as you call more functions, you're actually going to be going negative in the stack, and the higher numbers are considered to be the lower level or the lesser point in the stack, and the lesser numbers are supposed to be the higher values in the stack, if that makes sense. So once we do that, you want to create a function pointer called JIT function. Now this is going to be the format for calling JIT functions. We're not going to get into the JIT system today, but this is the basic format. Every JIT function is going to return a void, and it's going to take in a void pointer as data. And we'll see what that is at a later point when we actually call the JIT function and set up the system, but just create that for now. After that, you want to set up the priorities. So each thread priority, I think it's going to start with, I have no idea what it starts with, but this is why we call this function. So you want to set the thread priority basically to whatever the priority is set to at the time of creation of that thread. So I think for main, I think main actually has the highest priority, and then every subsequent thread has the default of regular, I think, or normal. I don't remember. But this is going to be based off of the high level as well. So you can actually set the default thread priority at the high level when you write your multi-threading platform in the language itself. So next you want to call setup. So setup is going to basically be where we set up the thread, obviously. Now take note that I do not set the state to running immediately at the top of this function. There's a very important reason for that. And the reason is because in the setup function, there's a potential that this can crash. So you don't want to set the state to running and have the virtual machine think that the thread is started and running when it's actually not. So if we go to start, and when we start a thread, you're going to see here that we have this wait for thread function. And this has a maximum spin count of 25, meaning that we're going to spin for a maximum of 25 times, and then we're going to basically give up after that point. So if the thread ended up crashing during the setup phase, then we're just going to basically spin out because we couldn't successfully create the thread. And we'll get that error returned back at the high level, which is why we want to actually do it that way. We don't want to get false flags in setting different states at the high level, thinking that the thread is started and running. So during the setup phase, you want to just do some basic setup. So you want to set the current function to null. Now you want to set these values. I honestly think this was used at a point where I could reuse the same multi-threading pointer, but I don't think I can do that anymore, but let's just go through everything. So you want to set the current function to null. Calls is going to be equal to -1. This is going to be the total amount of calls that we have in our programming language. So if you call main and then main calls another function, well, you're going to have two calls. But what this is going to do is this is going to actually be the calls, or the total amount of calls you've made, minus 1. So it's going to represent the index of wherever we need to be in the call stack. And if we want to figure out how many functions nested deep we're in, we just say calls plus 1, which will give us the accurate amount of calls that we've done. So you want to set that to -1. You want to set your thread signal to tsig empty. Please do this, it's very important. Otherwise you will break things. And of course we want to set up our suspended, exited, and terminated. Set our exit value to 0. Set up the JIT. You can create this JIT TLS setup function. If I go here to JIT, then click this, what does that do? TLS setup. Okay, so this basically sets up the thread local storage for the current JIT. So I get the current thread self, I set the JIT context registers to the registers for that current thread, and then I set the context of self, or the current thread, equal to, this value. So once you set up everything, then you want to initialize the thread. So you want to first create the data stack and the call stack. Now this is going to be the first example where we see how to set up actual memory in the programming language. So I allocate a data stack, I call calc, and I allocate an array of stack elements based on the stack limit. So a stack element is going to represent either a var or a object. So it's going to either be a number or a physical object. The reason why I do this is because if we have a number here, we don't have to allocate an object for every single number that we create. So it makes it a lot easier on memory, not to mention it's a whole hell of a lot faster in terms of processing power to manipulate this single var instead of accessing objects. This is one of the things that has made my language extremely fast by doing it that way. If you don't do it this way, then it's going to be actually pretty slow. So once we allocate that, that's not going to track the memory. So even though I have a check here to see if we have any space available to allocate the bytes that we want to allocate, we still need to update the memory inside of the garbage collector. So I say gc.add_memory, and that is going to update the managed bytes to the bytes that we pass in. And remember, this is an atomic integer, so we don't have to worry about thread synchronization if we're starting multiple threads. So that works perfectly fine. So if we go back out, so we want to add the size of stack element times the stack limit, and that's going to be the amount of bytes that we have allocated for this specific object. We want to do the same thing for the call stack as well. So you just want to create a bunch of frames and add that memory as well. Now, call stacks are, I think we've gone over this before. Yeah, we have. So call stacks are just basically a way for us to call functions, and it has these various different fields in here for us to facilitate each call. So if I go back, so once you set up the stack and the call stack, then you want to do a check. So if the current thread ID is not equal to a main thread, and this is important, you do want to do it this way. So if the current thread's object is not equal to null, meaning that the current thread that we're going to pass from the high level down to the low level, and we're going to check for a is class. So we're going to check to see if the current thread that we passed is a class. Then we want to create a string array by resolving the field of data and resolving the field of name. So we basically want to access name.data and then create a string array based on the actual thread that this instance represents. So this allows us to basically set up the name of the thread and go from there. And then you want to set up your frame pointer and stack pointer. So the frame pointer is going to represent the first item in the stack, and that's going to represent the first item in the stack after the thread locals. So if you don't have any thread locals in the programming language, the address of frame pointer will be 0. Otherwise, if you have, like, let's say 1 or 10 thread locals, the frame pointer address will be either 1 or 10. So it will start at the very starting point of that value. The stack pointer, however, is going to be negative. So it's going to be negative relative to whatever the amount of thread locals we have. So if we don't have any thread locals, the stack pointer will be here. Otherwise, if we do have thread locals, then let's say we have 3 thread locals, the stack pointer will start basically at the thread local before. So if this is the last thread local, then we'll start here, and then when we push something onto the stack, we're going to first increment the stack to after that point, and then we'll add whatever we need to add there. So that's kind of how it works. So that's why you want to have a negative stack pointer. Otherwise, if it's equal to the main thread, then we set the VM state to VM running, and then we want to add memory for the stack limit. That doesn't make any sense. Okay, so I'm going to remove that. That's going to save me a ton of memory. But yeah, so you want to do that, and then you want to set up your Sig Handler. Now, this Sig Handler is going to be a way for me to respond to signals in the actual programming language. I created this quick Sig Handler file, and we basically just listen for a bunch of signals. So we got interrupt signal, we have seg faults, illegal instruction, terminate, and abort signals. And all these are going to call the OS signal. What that does is that basically sets the signal status. And if the signal is not equal to sig interrupt, then I basically print the regs and I exit immediately. And this allows us basically to do listen for any pertinent signal. So if we did anything in our programming language, like let's say, we were executing some code in the main loop. So if we go to exec, did I spell it wrong? Exec. So if we go here to the main execution loop, and let's say the halt instruction was broken and it caused a seg fault, then that is then going to call the sig handler function, which is OS signal, and it's going to call a function called print regs. I'm also going to print out the signal as well, so I'll say signal to string, which basically takes a signal and returns the appropriate string value. And I say signal of whatever found, please contact the language developer. I mean, you can put whatever message you want, but the important thing is you want to know what signal you received, and then you can do whatever you need to do. So you can literally ignore any of these signals. You don't have to exit, right? If you get a seg fault, you can keep going. But I do want to exit because obviously if I get any of these signals, it's probably good to actually exit the application. So that's what I do. And print regs, this is where it gets into helpful hints. So if I get a seg fault, let's say, I'm going to print out all of the debug information that I need to see actually what broke in the programming language. And trust me, this function has saved my ass so many times for fixing bugs because I'll print out all of the register data. I'll print out the current stack pointer and the current frame pointer. And this is just going to be the numeric value of where it is on the stack. I'm also going to print out the current program counter and the current function that we're in. Now, with just this information alone, I can literally just go up here to my ODF file and search for the function, let's say main, right? And then if I go here to main, that's fine. This is fine. We can use this one. So if I search for main, and let's say I had a seg fault at instruction 21. So I can look at instruction 21. Oh, it's jump equal to 9. So I know exactly where everything broke and why. And if that's not enough information, then I go even further and I print out the entire call stack of the current function. So what led up to the exception? So sometimes this information isn't enough and I need to see what led up to a potential seg fault in my programming language. So I call what's called fill stack trace. Now, we're not going to go into this function right now because this is actually used by my exception system. So we'll go over that at a later episode when we talk about that. But basically, just picture this function, fill stack trace, filling up a string with a bunch of information about the current stack. And I say call stack, most recent call last. And I print out the stack trace or the back stack of all the functions. And then I print out if the current is not equal to null, then I print out the current function. Now this one is actually, okay, so I'm going to do function. This one's actually a bug. I should not have that there. It should be here. So yeah, so you want to print out the current function, and then you want to print out just some preliminary data on the stack. So literally, I'm just going to print out various different numeric values of data that is on the stack, and I do up to the 15th value. I don't really use this anymore. In the early days, I had tons of stack issues, but my programming language is pretty robust at this point, so this doesn't really matter. But if you guys want to see your stack, you can then choose to check to see if the data stack is present and then print out any preliminary data that you want. And yeah, so that's it. So once we do that, then where were we? So if I go back here, start. So if I go to start, and then if I go back down here to setup. So once you do that, once you set up the Sig handler, then that's it. We're ready to actually start the function. So now it's safe to set the state equal to thread running. And then we're ready to call the main method. So here's going to be how we execute functions. We're going to see how we call a function in the programming language for the first time. So what you want to do is you want to create a function called execute method, and it's going to return a function pointer. And of course, you know what the function pointer is. And what it's going to take is it's going to take a few arguments. So it's going to take the address of the function we want to call, the current thread that we're calling the function on, and then the JIT. So whether or not we're inside of a JIT. Now this is very important because as we're calling functions from the high level to the low level, we're going to be bouncing around between scopes. So we're going to be calling into native address functions. That basically means that we need to call this thread execute once more. But if we're just spinning inside of this thread execute and not calling any native functions, not calling any DLL functions, then we're not going to need to know or care whether or not we're inside of a JIT because we're just going to stay inside of here. So we're only going to call into execute if we're inside of a JIT function and we're calling into a function that isn't a JIT, or we are at the first point in our thread where we have no calls and this is the first function that we're actually calling. So the way that I do it is I have various different ways. So I have this setup method stack function and you can see it's right here. So what this function does is we pass in, the same data, and we basically get the method by adding the method's pointer to the address of the function, and we're just going to assume that this address is correct. We're not going to do any bounds checking, and then we're going to basically do a thread stack check on the current state of the thread. So what this does is we pass in the current thread that we're in, the stack size, and x, which is going to represent the address of this field here. So we're going to inspect the address of this local field to basically figure out, are we about to overflow the stack? So I check to see if the current thread stack pointer minus the current thread's data stack plus the stack size is greater than the stack limit, meaning that if we call another function, we're going to be over the stack limit. Otherwise, if the address of the address field that we passed in here, if we take that address and we subtract that from the ST floor or the stack floor, and we're going to check to see if this value is less than or equal to the stack overflow buffer. So this is going to be a buffer, a random buffer that's basically going to look at the stack and it's going to see if we are in that zone. Obviously, we're never going to hit the buffer exactly. And let's say our buffer was like 10 kilobytes or whatever. We're not going to always hit the 10 kilobyte value exactly. So we may be a little bit over, so that's why we have this giant buffer. And if we end up having whatever the specified amount of the overflow buffer is, and we have less than that value, and if so, then we throw the stack overflow exception because obviously we're nearing the physical limit of the actual thread stack or the imaginary limit of the stack as well. So that's how that works. So that's what we do. And so now here's how we actually call a function. So I add a new entry into the call stack by plussing calls, and remember it's going to be -1 from the start, and I initialize a new entry into this array. So what I do is I pass in the current function, which is the current function that we're in. I pass in the current program counter, the address of the stack pointer minus the stack pointer offset, and the frame pointer, and whether or not we're inside of a JIT. Now, here's how it works. This might be a little bit confusing. Whenever we call a function, let's say we have a function of, I'm actually going to go to a real example. I'm going to go to my tests and my syntax. Now, let's create a function in here called foo. And in that function, I'm going to, let's say, have an argument of var, right? And we're going to just call it x. If I go to call foo, and let's say I put 4 in there, right? So if I put 4, this is going to take up stack space of that value. But there's a problem with that. Before we actually call the function, we need to push the value of 4 onto the stack, right? So now this value is going to be onto the stack. So we need to figure out what is the quote unquote reset value of the previous state of the stack before we called this function. Meaning that before we called this foo function, we had a stack address of 1 because obviously we have one field. So if the current stack has just the args field in there, we want to reset the stack pointer to args, not to 4, right? So what we do is we say stack pointer minus the stack pointer offset, which is going to basically just represent the amount of arguments that we have for our function. So that way we can appropriately reset the function address. So that's how we do that. And then of course we just say whatever the frame pointer is, because frame pointers don't change until you actually call the function. And then again, whether or not we were a JIT. So, and then after that, we want to set up a few other things. So we're going to set the current function. We want to set up the cache equal to the byte code of that current method. We want to set the frame pointer equal to the stack pointer minus the frame pointer offset. Now, this is going to be a bit different. The frame pointer offset is going to depend based on whether or not we have an instance function or a static function. If we have a static function, that means that there's no instance here. So when we call foo, the entire argument space for foo that we're going to need to push on the stack is just going to be this one 4 value. If we have this as a instance field or an instance function, we're going to need to pass on the instance, inst, so I'm just going to put that for short. We're going to need to pass the instance before any arguments that we pass to the function. So we need to basically set the frame pointer equal to this value of this point instead of setting it to 4. That's why we have a different offset value for frame pointers and stack pointers. Also, another thing you need to consider is what happens if we return a value from an actual function. The way return values work in a function is we don't allocate an additional, cell for that return value as a potential address, because that just wouldn't work. There is a universal way that I access the instance of every single function, and it's always going to guaranteed to be field address or frame pointer address of 0. So we can't do that. So what we do is when it comes time to return, we actually just set the value right in the place of the instance. So if I return 0, when it comes time to return the value, I just put 0 in the same stack location as the instance value. So then that way, when I return out of the function, I can either take this value and assign it to a variable or immediately pop it off the stack. So we'll see more of this as we kind of go along in our development of our programming language, but that's the general premise of how it works. So depending on those parameters, depending on whether or not it's a static function, depending on whether or not it returns a value, depending on how many arguments that the function has, will all determine what the value of the stack pointer offset and the frame pointer offset will be to make sure that the stack is appropriately aligned based on the data points that we were provided. So just keep that in mind. That's kind of generally how I call functions. And then I plus get the stack pointer to the frame stack offset. Now, what a frame stack offset is going to represent is, let's say we have this function of, foo with our var. Let's say we have a local variable in here of y, right? Now this is going to need to allocate more space for y. So if we go back to our example here, right? Let's say the foo function was an instance. We're going to have inst here as the index of 0 or frame pointer plus 0. Now we need to update the stack pointer. So even though the stack pointer currently is pointing to this cell, we need to allocate additional space for any other variables that we're going to have inside. So we're going to plus get it to the stack offset or the frame stack offset, which is going to offset the frame to however many items or however many local fields we have for that function. So we're going to have y here. So now the stack pointer is going to be set to here. And if you guys remember, anytime we push something on the stack, we always plus get the stack 1 value, and then we put whatever, data we want to put in that stack address. So that's kind of how that works. Hopefully I didn't confuse anyone. And then finally, we want to set up the PC. That's going to be equal to the cache. So the basic way of how it's going to work is as we're executing instructions, and here's like if we have this y equals 10, we're basically going to start out. So let's say we have instruction here, this one, this one. Basically, we're going to start at instruction of 0, and we're going to have the program counter point to the physical address of the actual instruction that we're going to be executing, and then we're just going to plus it each time to basically jump to the next instruction. So that's kind of how it's going to work. So that's why I set it to the address value, and a cache is just a reference to an opcode instruction, and an opcode instruction pointer is just an unsigned int. So that's going to represent the format of our instructions. So once we do all of that, then I think that's it. So once we set up the method stack, then we want to do our JIT fancy stuff. So basically what our JIT is going to do is we're going to check to see if the method is not JIT. So if it's not JIT'd yet by the just-in-time compiler, Then we want to check to see if we've branched more than the JITIR limit. So if we've branched around the function more than X amount of times, currently my limit is 25,000. If we branch more than 25,000 times in the actual function, then that allows us to basically JIT the function. Branches are, of course, expensive because it messes with the CPU and it makes it more difficult to perfectly align instructions one after the other. So what I do is I check to see if the method is not compiling. Basically, once I set a function in motion to be compiled, the compiling Boolean will be set to true. So if it's not compiled and the JIT attempts is less than the JIT max attempts, and yes, you can fail to compile a function. There are reasons for that. We'll see it later. So if we haven't failed more than the maximum attempts, which currently I have 3, then I send a message to the JIT by passing in the reference to the actual method that we want to call. Now this was referencing old code, so I'm actually gonna create a method field here just for this value. Okay, so after we send the message, and we'll jump into that function in a little bit. Otherwise, if we are less than the R limit, then we also update the branches. So not only is it referencing how many times we've jumped around in the function due to if statements, for loops, whatever, it's also how many times we've called the function. So whether or not we've called the function, jumped around, whichever comes first, more than 25,000 times, we will compile it. Now, after we do that, then we're going to check to see if the method is JIT. Now, there's a high chance that right after we send the message, as soon as we get down here, it's not going to be JIT'd. So most likely, the next time we call the function, it will be compiled correctly. Then we want to set the JIT context caller to the current method up here that we're going to be calling, and we want to return the actual JIT function. So we want to return method JIT function, which is going to represent the actual function that's going to be set by the JIT compiler. So once it compiles successfully, we're going to set a reference to the actual address of the function in memory that we can execute that has been compiled down to machine code for the specific machine. And that's it. So now let's go to the actual JIT code, and we're nearing the end of the video here, so we should be done shortly. But what we do for sending a message is we just check to see if self is not equal to null, and self.getAssembler is not equal to null. Self is going to represent the actual reference to the JIT system. So up here we create a new JIT pointer, so that's what that is. But then we check to see if the assembler is not equal to null. That's just going to be a reference to the assembler object. We'll get into how that stuff works later. And then I basically just put a recursive lock, so I can actually just use guard here, G-A-R-D. So we're going to guard the mutex, and then we're going to say compiling is equal to true, and we're going to add a new value to the message queue. So we're going to push that value back, and we're going to just add the function's address to be compiled by the JIT. And that's it. So once we do that, then we've executed a method successfully. And now we're going to do a check to see if our JIT function is not equal to null. Now, in the case where the function is a JIT function, then we're going to actually return that address here, and it's not going to be equal to null. Otherwise, if we just executed the function as normal, then we're going to return null as the value. So that's how we kind of know. And if I go back up, so depending on that, if the JIT function is not equal to null, then we call that function and we pass in the reference to the JIT context from the current thread that we're executing in now. Otherwise, we try to catch an exception, and that's it. So that's going to be it for today, guys. I don't want to drag the video on too long. After this, we're going to be getting more into our main execution loop and, catching exceptions, how to shut down a thread, and more. So there's a lot more to come, but hope you guys enjoyed the video. As usual, if you have any questions, as always, put them in the comments section below. And of course, if you guys would love to help support the channel, you can always head over to my GitHub repository at andrewdevc/sharp. And when you do, definitely watch, start, and fork this repository. That gives this language a lot more visibility and let other developers know this language exists. Also, if you're curious about some of the stuff that I've been up to recently or some new stuff that I'm looking to add in the future, you can always head over to the roadmap. This is a nice way for you to see in real time kind of what I'm working on with the programming language and what are some of the new things that I'm looking to add in the future. So hope you guys enjoyed the video. As usual, if you're new to the channel, definitely consider subscribing, and until next time, I'll see you guys later.